Okay. So, hi guys, you already know me. I'm Oscar. You guys know me mostly about the React Native stuff, but today I wanted to talk about something I've been doing lately, which is trusted execution environments. With me is Steve. Steve is a coworker of mine, so maybe you can do a little bit of an introduction.
Yeah, I'm Steve. I work with Oscar at Opacity. I'm originally a mechanical engineer and got very interested in crypto and ended up meeting Hirsch, and they brought me on. That's a CEO. Um,
Nice.
yeah, here we are, a couple of years later.
Nice. Yeah, so I was doing a lot of React Native before, and then I started doing Rust, and one thing led to the other. I ended up talking with Aaron and Hirsch, and over the last year, I've been helping the team, been working very closely with Steve when it comes to the Rust side of things, and that kind of led me to work with trusted execution environments, which is what I want to talk about today. Steve, you have a little bit more of an expertise, so maybe you can do like the very simple introduction to what a trusted execution environment is.
Yeah, I definitely would not call myself an expert. I've got, about a year on this, but, very, very hands-on year. Um, so yeah, trusted execution environment is a way to run code that you can verify exactly what the code is you're running. I usually like to frame it as we as the company or the developers, we are protecting the users essentially from us or from our ability to um, change the rules, to take data that we're not supposed to take, to rearrange information, or do anything outside of what you know if you look at the code as sort of an agreement between the developers and the users. The T's enforce that agreement. Sort of how
Right.
I think.
Right. So basically, TEE is a technology that's baked in the hardware that allows you to do verifiable computing. Right. It allows you to extract or verify in a way the code that you say it's running. It allows you to check that it's actually running that code. Right. So it's actually a very the base technology is hardware based. Right. So there are different flavors of this. We have SGX, TDX, we have ARM Trusted Zone, right? But we are using the Intel flavor, which is SGX, right? So
Right.
maybe we can start talking a little bit about SGX. Um, maybe you can start with a little bit what SGX is, like how does it work on the metal side of things.
Yeah, so SGX is Intel's brand of um, Enclave. It's a little different than some of the others in that it's sort of the minimalistic approach. You're with SGX, the Enclave, the TCB, the Trusted Computing Base, is just the software that you're running, right? So if we write a program, that's what's in the TCB, and that's what's being protected by the enclave, as opposed to some of the newer versions, Intel's TDX. I always forget what AMD is called, um, but it's two acronyms with a hyphen in between.
Mm-hmm.
um, but that's the full virtual machine runs inside the enclave on those. So it's a bit easier on the developer because you can just write code and it just runs on on Linux. It's fine.
Mm-hmm.
The whole thing is there. Whereas SGX, you have to do a little bit of work to get around the calls in and out of the enclave, which are essentially not allowed by SGX.
Mm-hmm.
And the package we've been using to do that is called Grammy.
Right. So it's not only like a CPU element, it also protects memory, right? Like you can reserve an amount of RAM, and it also gives you some extra guarantees that no other process, like not only the OS guarantees, but hardware backed guarantees that no other process will be able to access the memory, right? It really like secures your application from tampering from the outside world, and it also gives you the guarantee or the way to prove the code that is running on the secure enclave.
Right. Yeah, those are the basic guarantees. And also, like secret provisioning, right? Like I can have a signer generated inside the key, and that way, we know that information signed by that signer came from a legitimate enclave.
Cool. And I think next we wanted to talk about applications of TEs, right? So,
Yeah.
from my understanding, TEs are very hot right now in the crypto world because they allow you to do this kind of verifiable computing without spending the huge amounts of like energy and computing required for like normal on-chain operations. So it's kind of a escape hatch from the traditional on-chain paradigm of like doing computing, right? So it's very useful if you need to do some sort of operation that you don't want to spend like gas or ether or whatever, but you still want to be able to give the guarantee that you're not doing anything funky with the user data. That's a very common application on the crypto side of things. Then we also ran into what WhatsApp is doing, which is very interesting. WhatsApp now is doing AI summaries of your chats, but you can imagine that's a very iffy when it comes to user privacy, right? Like they need to be able to access the text of your chats to be able to feed it into an LLM. So what Meta and WhatsApp have been doing is basically they created a TE environment for them to send your messages, and you can see what they're doing with that data. They're feeding into an LLM to get a summary, but it's like kind of end-to-end encrypted, right? Like it arrives encrypted into the TE, then they do the computation, they run it through the LLM, take the output of that, and then they encrypt it back again, and then they send it back to your device, right? So that gives them the ability to do these summaries, but in a trusted execution environment, so you can see it's like, okay, they're not doing anything else with the contents of my private messages, right? Like they're not storing them, they're not analyzing them. All they're doing is giving me this summary of the data. I don't know. Do you know of any other application out there?
Um, there's, in crypto, there's sort of two main groups of applications. There's like these private blockchain, secret network, and Oasis that use TEs. So that, distributed, as a distributed system, anyone can run a node and it runs in a TE. So they don't get to manipulate or see the state because of um, so that allows private state blockchains, and there's more of those, but I can't. Those are the two names that come to mind. And then also like what Flashbots and Unichain are doing, they use it for ordering so that the the transactions in the block are ordered in a fair, the, one of the things in blockchain, one of the like ways value is extracted is whoever's building the block can order the transactions however they want. They can put their own transaction in a place that's profitable, that is essentially bleeding value from users. And so these are sort of tools against being able to do that. Those are the two main common uses in crypto. How we sort of started on that, the TE path, was we wanted anyone to be able to run one of our nodes, and we were doing a multi-party computation process, and
Yeah, that's also
there is
That's
What's
also
that?
cool. That's also cool use case, right? That you can write the software if you make it open source. Um, you can make out of ordinary people operators of your software, right? Like there is a
Right.
way to verify that they are really running the stuff you gave to them without modifications.
Right. Yes, exactly. And that, collusion is the vulnerability in the MPC, and this
Hmm.
explicitly prevents against any sort of tampering, including that collusion.
Yeah. I don't remember what's the next point we wanted to touch.
Let's see. Well, you have the sort of the list here that mentions secure voting systems.
Yeah, let's not do that. Let's never use computers to vote, but what's
Right.
next?
So we got, limitations and known attacks is um, the known attacks, I immediately, the side channel attacks for SGX, Intel, my understanding at least is Intel is sort of declared these are outside of the scope
Mm,
of what they're protecting against. This
mm,
isn't part of their threat model. Essentially, it allows people to extract secrets from the enclave if they have access to the physical machine, if they're um, if the machine, if it's a server machine and they are running software that co-inhabits the same, actual physical device, or if they have
mm.
hypervisor access, there's ways to do little tricks, and there's several different attacks that have been published over the years. Um,
Right. So it's not really bulletproof, right? Like at the end of the day, it's still the same CPU. Like there is some hardware protection, but whatever, if an attacker gets a hand of your hardware and can do, timing attacks or power consumption attacks or whatever, it's like, at that point, you cannot protect against everything. So whatever I guess applies to a normal Intel CPU would also apply to an SGX enclave CPU.
right, and then this is where making sure your version is you've got the latest version, you've got the latest BIOS, so everything's up to date. Essentially, becomes really important in
Mm,
the SGX
yeah.
environment.
Yeah, and I guess when it comes to limitations, this is also something that we have both been suffering through the last few months. There is like not very extensive documentation, and whatever is out there is kind of low level because it's everything is vendored, right? Like each CPU producer manufacturer has its own quirks. It's very low level technology, at least SGX is. So we do have like a lack of documentation there. We also have gone through a lack of what would you call this, like error codes. Sometimes it just fails or it does something funky and it doesn't really produce any output whatsoever. So you kind of left there scratching your head and wondering, like, okay, what did I really do wrong? There is also the lack of like multi-threading was something that we kind of have suffered through because it's not explicitly clear what could go wrong. Like it's kind of there, it's mentioned a little bit in the documentation, but it's not straightforward, right? It's like, okay, if you have an allocation problem and then it's like, okay, if you're not looking at the assembly code or profiling memory or this kind of stuff on a day-to-day basis, it just feels kind of random at least.
Right, and then that was one because I struggled with that one we both did, but for quite a while. And I was, even able to surface the very low level error that it was something with the glibc malloc, you know, and that's not something, I'm not used to going that deep in the stack, right? Like
Yeah.
I don't have a lot of like experience with what that is. And then in the grounding documentation, it's under performance. It describes it as or performance improvements or something like that. It describes it as pathological performance, which I love that description. But it's just sort of like I have no idea what's going on. It's failing sometimes with this like very for me at least, esoteric
Mm.
uh, code, or sometimes just completely silently.
Yeah.
Um, and so, the multi-threading and finding being able to limit the glibc malloc arenas, um, how
Yeah.
many threads you're allowed to have those. And we've been limiting that to one, which is
Yeah.
what is suggested in that
Yeah.
documentation.
Yeah, but even if it wasn't the documentation, it took us like a long time to really understand. It's like, oh, okay, this might be the thing that is killing the performance in our application, right? And
Right, and there were other little things we learned along the way, right? Like the size of the enclave, the threads available to the enclave, the stack size in the enclave, which actually, that for some of the testing we were doing while we were running what ends up being multiple different machines, different enclaves all in one during the test.
yeah,
Um, we were hitting the stack size limit.
yeah,
Um,
yeah.
and
So it
that's
took us
that does.
just a lot of error and trial just to try things. And it's like, okay, this kind of seems to improve things. It's like one step forward, then move to a different machine, different error or different behavior, and so on and so forth until we're kind of in an okay-ish place now. But like I said, we don't get error codes when something fails, which is like feels magic box. Who God knows when something might pop up. So we will see. Um, I mean, I guess we haven't mentioned this too much, but we are doing this in Rust, and we're using Gramine. Maybe now would be a good time to talk about the tools that we're using. Um, so ideally, you can run whatever code you want in this SGX machine, right? You would need to import the Intel libraries, and you need to compile your application in a way that you use a manifest, where it's like where you declare all the resources that you want, you declare the variables that you're going to have access to, and that gives you a hash, a stable hash of like the whole snapshot of your program, plus your environment variables, plus the files the program has access to, right? So if at any point you change anything of that, the hash, the machine readable enclave that we call it Mr. Enclave, that will change, right? So that gives you the guarantee of what you're running, the code that you're running on the machine. So again, you could program in anything, right? Like you could do it in C and C++, but we're doing it in Rust. It's like kind of the modern stack of doing like native, like low-level programming, we could say. But you have a little bit more expertise on Gramine, so maybe you can talk a little bit about Gramine. You know, graphing was before, what it does for you on top of SGX. Maybe you can go a little bit into that.
Yeah, and it's the main thing it does is there's a lot of overhead in running an SGX enclave in terms of it does not have access to your operating system. So any communications that it needs to do, it needs, something needs to handle that communication for it. And grabbing sort of that bridge between either your operating system or anything external to the enclave, allowing it to do those communications. Which obviously there's a lot of potential foot guns there. Just you're building secure software. What's in the enclave and then what you allow across that boundary is there's sort of a potential vulnerability, right, on every single uh, thing you allow through, right? And you mentioned the Mr. Enclave, right? So any user should be able to generate that same Mr. Enclave. They should be able to generate that same hash from the same code with the same dependencies. Everything that's in that enclave should be completely repeatable for anyone who wants to verify that. which then
Right.
can get tricky when you update dependencies and stuff like that, because that every single thing that changes will change.
Right. Right. Um, yeah. So Gramine is the tool, the framework that simplifies our life a little bit, right? We just compile a program, we run it through Gramine, and that runs the program as is on a SGX machine. That's kind of the gist of it, of the tool that we use. But now would be interesting to talk a little bit how does the actual verification work, right? And what we're doing on top of SGX. So this is where we come to RATLS, right? And how we build the services. So we basically take our code, which just to give an example, it would be HTTP server, right? That takes the request, will do the computation, will give something back to the user. So that we code as a normal HTTP Rust program server. But on top of that, we use the artifacts that SGX gives us, right? So whenever we establish a TLS connection, what we can do is we can reach into the libraries of Intel for SGX, and we can generate the attestation quotes, right? So an attestation quote is basically the hashes of the software, of the hardware, some certificates of Intel that actually allows us to generate signatures for all the stuff that we're running, right? So we can basically say, here from my client that might be or might not be an SGX machine, I want to connect to this service, but I can do some verification before it starts sending data, right? So I do like the request, and I'm going to get like nonces and the attestation quote and stuff, and I can really verify it's like this server is running the software that I expect it is running, with a guarantee that it's not being tampered with, right? And then once I have verified all that information, then I can start sending data to the server.
Yeah, and I guess now would also be maybe a good time to mention Mr. Signer. We've been talking about Mr. Enclave. There's Mr. Signer as well, which is a hash of a public key of whoever created the enclave, whoever wrote the software. When they build the enclave, they can sign it. So you can say, okay, we know that this code came from this company. So you can know, it is this code. Mr. Enclave tells you this is the code. Mr. Signer tells you, here's who wrote it, who or compiled it at least, and both of those can be used also to seal keys in the enclave. So any information that you want to persist through, new startups, you can persist in the enclave, and then if it's sealed to Mr. Enclave, only the exact same code can unseal that key. Or Mr. Signer can be used, if it's sealed to the signer, then
only the authorized party can decrypt the data.
Right. Which you're giving. My original framework was, right, we're protecting the users from us, essentially, right? Like, you have some assurance that what I can do is limited. Once you start using that Mr. Signer, that sort of breaks, right? Because I can write whatever code I want and sign it, and then access that Mr. Signer. So then that comes into sort of the same thing around RATLS. You can choose what fields you want to verify in that attestation. Right? Pretty sure you want to know that it's a legitimate SGX enclave, and that's verified through sort of a certificate authority chain that traces back to Intel. And there's some, don't want to probably get too deep in the weeds, but there's, PCCS, a bunch of acronyms that,
allow you to verify like every step of,
right,
of the stack.
Exactly. And so then the RATLS tells, the attestation quote in the RATLS allows you to say, okay, yes, this is a legitimate enclave. It's running, this code by
Yeah,
this developer.
yeah,
And you can choose to, value whichever ones of those are important to your application.
yeah. And that brings us to a very important point, which is like you need to open source your code, right? Because that's the only way for the users to, like they need to be able to generate the hash of the code with all the configuration of the server and the environment variables, yada, yada, yada. I mean, there's some escape hatches, like you said, like Mr. Signer. We can also like choose pass-through for some environment variables. That means that they won't affect the hash that is produced by the code. But at the end of the day, that's the only way for users to be able to verify that you're not doing anything nefarious with the code, right? Like you need to be able to, you yourself generate the hash and then you compare it to whatever is running on the server, plus all the guarantees of like the certificate chain and PCCS and yada, yada, yada. And then you yourself can, be convinced it's like, okay, this server is really running that piece of software. I'm sure it's not doing anything nefarious, and I can really send data to it, right? Like that's kind of the whole point of doing all of this, right? Like this verifiable computing is for you to be able to verify the code itself.
Right. It's been all sort of a paradigm shift for me, like how to think about developing in terms of these security parameters, right? Like it's not intuitively obvious to me that using, Mr. Signer breaks some of the security guarantees. It might be worth mentioning Andrew Miller is the one that he was very helpful in us getting up to speed on a lot of this, and he's the one that sort of pointed that out and laid those things out to us. He's oh, I should have brought this up. He's an associate professor, I believe, at University of, I want to say Illinois, but he's with Flashbots, and he's done a lot of key security research stuff.
Yeah.
And it's also the WhatsApp, right? The Trail of Bits. I think that sort of fits in here nicely. That Trail of Bits audit, the one finding on there that I really glommed onto was right.
That told us a lot of things.
Right. So we've mentioned, side channel attacks. So I've got the secret, and that can be leaked. So that'll be, for example, your TLS signing key that you're using for RATLS. So if that's leaked, I can impersonate a live, an enclave. I can use that leaked key and a stale, essentially an old attestation from that enclave. I can use those two together to make, to imitate an RATLS, a valid RATLS connection. So the way they got around this is basically doing what they call a freshness check, that you use a nonce to say, okay, this is a live, this is a live enclave that signed this nonce. So I provided this nonce and it signed it and gave it back, which we tried that, and at least in our initial implementation, that sort of allowed the same type of attack. You still don't know that who's signing that nonce is. They can run the valid software to sign the nonce, and if they have that leaked TLS key, they can still.
It gets complicated, right? Like I don't want to get too deep into the technical terms, because you really have to look at the code and understand like how TLS works and yada yada yada. But like once you have like a company like Meta, Facebook, doing one of these verifiable services, like you're going to get eyes on it. And there are security companies that do this like audits, because it's good for them too, right? Like they get their name out there. It's like, look, we found a security vulnerability in this service from Meta, And we found this article from Trail of Bits, which is a different company that did a security audit, and that taught us many things, right? Like when we started, we were like, okay, it's enough for us to extract the Mr. Enclave, the signature of the software, and then people will be able to verify it. But once you start getting really deep into it, you come into all of these cases, right? It's like, okay, once I have the signature, I could impersonate your server, so you have to put a nonce into it. You have to guard against side channel attacks. Like there are some protections that you can do, which I'm guessing security researchers who might be watching this will be like, oh, these guys are stupid. They don't know what they're talking about, right? But we kind of are, right? Like we got into this not from a security research point of view, but from like, okay, we kind of need to do this verifiable computing. So it's a rabbit hole for sure, right? Like you really go deeper and deeper down the stack and the layers of like CPU and memory and network and TLS and yada yada yada. So there is a lot of things you need to get right.
Right, and that is how we ended up solving this, was using actual TLS session key material, EKM. But we actually use material that's unique to that session. And so we had to use some lower level primitives to make that available. And then you can guarantee that yes, this attestation came from this session. And so this really is a real enclave, and now I do know that it's running the right software.
Yeah.
On and on.
Yeah. There are a lot of things to get right for sure, and took us a couple of months of just like pain, because like I said, at some point the documentation is a little bit missing. So it's a little bit crawling in the dark some days. Other days it just works.
And a lot of this, at least that I'm aware of, there's no like standardized documentation that says, oh yeah, if you're doing RATLS, because there's RATLS packages, right? Like that's more or less out of the box. But then the expressionist check, like I didn't think of that. There's nothing telling me that, oh, that's a thing until you found that report. And that sort of opened my eyes. The other things in that report was essentially what you allow in the enclave. Right, which is, Yeah,
and also you can take a look at our code from like many months ago, and it was kind of awful terrible, right? Because we were doing things by hand, more or less, and little by little we started coming up with abstractions like middle layers for HTTP server, middle layers for like our clients, like non-SGX and SGX that connect to an SGX machine. Yada yada yada. I mean, there's just a lot of complexity there that we have learned a lot of lessons. Before we also didn't have testing infrastructure, right? Because it's very easy to kind of delude yourself into thinking, okay, whatever I run on my machine will run on an SGX machine, and we learned that at some point. Like, no, that's not true. Like, we really need to run on the hardware to get like proper behavior, metrics, stress testing, yada yada yada. So there were a lot of lessons learned as we went developing the thing.
The one, and I don't remember how, I remember you found, after I spent months on it, you found the solution. But the deterministic build.
Yeah, the compilation steps for some C library that we have.
Right, so it would, on different machines, we'd get different Mr. Enclave values, which breaks the security guarantees and all of that. So that was another whole adventure.
Yeah, that one was a fun one, right? Because we just didn't know. I mean, we had it was the program that we were working on at the time, and everything was working for like a couple of months. And then after like a week of working, we started merging work, and then we started getting different Mr. Enclave values, which is again the hash of the whole program. On different machines, but it wasn't failing. It was working as intended, but it was just giving us different hashes of the thing. And that took like some spelunking down several rabbit holes. Like we were at first blaming SGX, and it's like, okay, there has to be something that we're doing wrong there. But as it turns out, it was like a Rust dependency that we had that was compiling some C files. And in order to compile the C files, I mean, now we get into the Rust hole, right? Like it uses a compiler that is running, like embedded in the Rust dependency that we had. But in order to use that compiler, it would just read the contents of the disk and then pass those into a command, like gcc blah 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 blah. These three files. The error was, or the problem was, whenever Rust was reading the contents of the file disk, it wasn't deterministic, right? So on one run, it would read A.C, B.C, and C.C. And then in a different machine, it would first read B.C, A.C, and C.C. Right? So just changing those files and how the C compiler works, it will generate the table of symbols in a different order, and that changes the hash of the final program. But it's like, okay, how can you know this, right? Like, how can you tell this when you're trying to program at a high level and your own code, everything works fine? Just trying different things, right? Until you find the culprit.
And then there's, also like what guarantees do you want? What do you want? Because the manifest allows some flexibility on what will change that Mr. Enclave file. So what do you want? What guarantees are you giving your user essentially?
Yeah.
So what do I have the ability to change on the fly in
Yeah.
terms of environment variables? They've got
Yeah.
what's called trusted files, which get hashed into the enclave.
Yeah.
And then allowed files, which are just basically allowing through.
Yeah.
And then Gremlin will give you a warning if you have any allowed files that, basically, hey, don't do this.
Yeah. And I guess that will have to be like a conversation with your users, right? Like the people who are using your service. And at some point, somebody will complain because somebody always complains. But it's like, okay, this is what we can do to give you enough of a security guarantee that we're doing nothing nefarious. And if you are not happy with that, then feel free to find somebody else. But there are limits at the end of the day to what you can secure and at the same time provide. Right. Cool. I don't know. Is there anything else you want to add?
Is it worth touching on, running it through Docker versus running it on bare metal? That's sort of our most recent.
Yeah, we're still kind of going into that rabbit hole too, right? Yeah, because if it's hardware backed, like virtualization of the hardware calls might introduce some funkiness in there, right? And that paired with all the undocumented kind of unknown behavior that we have had over the last couple of months, we're now exploring the idea of not running the code in a Docker container, which is like, I think, standard nowadays for deploying server code. Yeah, and I think that's worth considering if at some point you're going to run one of these TEEs and write your code for this TEE service. Yeah, exploring the idea of running it on bare metal might be something you need to do because of the hardware guarantees, right?
Yeah.
Other than that,
and we got some performance improvements doing that also, right?
At least for now, it seems that way. Like we're both not experts on this, right? Like if you really, really want an expert, you need to go to like Intel engineers that deal with the hardware, or maybe somebody like Andrew Miller, who's like very research oriented and knows the ins and outs of like these various systems. We have now been focusing a lot on SGX because that's what we're using, but you can imagine that different services will have different sort of trade-offs and pitfalls and different behaviors. I know AWS gives you the Nitro, I think is the service for this like TEs. I think that's based on AMD.
Well, the Nitro's a little bit different. My understanding is, although there is a hardware component to that, it's not really hardware based, it's hypervisor based. And so it's at least in my mental model, I haven't dug too deep into it, but it's more like a password manager that allows, execution.
Okay.
It's a little bit of a different model, but it's, widely used by very big companies. I think Visa and
Yeah.
how others.
Yeah. Yeah, I guess that's the conclusion, right? Like it has a lot of pitfalls. It might have a different problems and depending on the system, on the services that you're trying to use. But if at some point you have the need to do some sort of computing where you need to give a strong guarantee of like doing nothing nefarious, of running certain code, this is the tool to do this. Cool. I think that's it. I think we're already 40 minutes in. We already gave a pretty good overview. We could be here and talk like the very minutiae, line by line, but
there's lots of rabbit holes.
There's lots of rabbit holes. Okay, cool. Then thank you, Steve, and
yeah,
maybe
thank
we'll
you,
be seeing
Oscar.
each other next time.
Yeah.